Okay, so as I said in this video, we're going to look at, sorry, my mind's just spacing a little bit here. I'm pausing. Sorry about that, I actually just had a small pain attack, but I'm over it now. So, what are we talking about this time? What we're going to be talking about is solving the differential equations. And so before we even dive into the circuit, I want to just give us a couple examples of how we solve these kinds of differential equations. So, and we might not even get into LC and RLC circuits today, and that's fine because honestly, this chapter 8, which we're going to spend some time on, is the last chapter that we have to get covered in this semester. So we're looking pretty for this. So I'm going to go through some of this stuff maybe a little bit slower than I normally would. Alright, so what do we have here? Well, let's look at an example. So I'm just going to have x double prime plus 5x prime plus 6 equals 0. And then I'm going to give us some initial conditions. X at 0 equals 4, and then x prime at 0 equals negative 2. Now those are just some random numbers I picked. So to solve this, remember our first step is to write down the characteristic equation. So what are we going to write down here? Well, this would be s squared plus 5s plus 6 equals 0. And then what would you do? We'd factor this as s plus 3 times s plus 2 equals 0. And then we of course get s is equal to negative 3 and negative 2. So we have two distinct roots. So I'm just going to scroll back here a little ways. Distinct different real numbers. We know that the form is a1 e to the s1t plus a2 e to the s2t. So I'm going to write that down here. So my solution, so x at t, because that's the variable we're looking for here, x at t is going to equal a1 e to the s1t plus a2 e to the s2t. Now it doesn't matter which one you make s1 or s2, it will just flip whatever the constants are as far as a1 and a2 is. So it doesn't really matter what you make s1 and s2, so we don't have to worry about that. So I'm just going to plug them in the order I have them written here. So a1 e to the negative 3t plus a2 e to the negative 2t. Okay, so that's what we have now. And now I need to figure out what a1 and a2 are. Well, we are given that x at 0 was equal to, and I don't remember what I said it was equal to, 4. So we'd get 4 is equal to a1 e to the negative 3 times 0 plus a2 times e to the negative 2 times 0, which of course would just be 4 is equal to a1 plus a2. And then if we go for the next initial condition, it's that x prime at 0 is equal to negative 2. So we should figure out what x prime is. X prime is equal to negative 3a1 e to the negative 3t minus 2a2 e to the negative 2t. And so we'd wind up with skipping the one step we had here. Negative 2 is equal to negative 3 a1 minus 2 a2. Now we have two equations, equation 1 here, equation 2. We could go ahead and solve these using one of technique we want to, I'm actually just going to go ahead and multiply this equation by 2 because I don't want to have to drag my calculator out right now, and you get 8 is equal to 2a1 plus 2a2, and then you have negative 2 is equal to negative 3a1 minus 2a2. Add those two equations together, and you get 6 is equal to negative a1. So a1 is equal to negative 6. And then we just use one of those equations. I'll just use equation 1 here. That 4 is equal to a1 plus a2. So 4 is equal to a1 plus a2. And so then we'd get what? We'd have 4 is equal to negative 6 plus a2. So a2 is 10. And so we'd write my final solution down at x at t is equal to negative 6 e to the negative 3t plus 10 e to the negative 2t. Alright, so that's our first example problem. And what I'm going to do here is do an example problem for all of the cases that we could have here, just to illustrate them all. So, and while we're at it here, because this is going to be important for us to be able to identify, this would be overdamped. And we know that much earlier in the problem because we know if you get two distinct real roots, that's overdamped. Alright, so now let's move on to the second example here. The second example, let's look at x double prime plus 4x prime plus 4x equals 0, and we'll say x at 0, in this case we'll say it's 3, and then x prime at 0 we'll say is equal to 5. Again, I'm just pulling these numbers out of nowhere. We'll talk about how you figure out what the initial conditions are when we're actually looking at RLC circuits and LC circuits. They'll either give you the initial conditions, or we'll have to do some circuit analysis like we did with the RL and RC to figure out initial values. Alright, so what do we get here? Well, my characteristic equation is s squared plus 4s plus 4 equals 0. Now if we factor this, this would be factored as s plus 2 times s plus 2. So we'd get s is equal to negative 2 comma negative 2, which clearly you don't have to write it down twice, but the reason I'm doing this is we have one repeated root. So one repeated root means then that we would get well, first off, we're in the critically damped situation, and we'd get the form of my solution. I'll go ahead and write it kind of like the book does, except let me write it correctly. a1 plus a2t e to the st. So that means my solution for this equation is going to be in the form a1 plus a2t e to the negative 2t. Now, just like we did before, we have to use initial conditions to figure out what my constants a1 and a2 are. So let me scroll back up here because I have a very bad memory right now. X at 0 was 3, so we have 3 is equal to a1 plus a2 times 0 e to the negative 2 times 0. But what we can see here, this is actually kind of nice, is we actually get right away that 3 is equal to a1. Now, to figure out a2, of course, we're given the initial condition for the first derivative, and this is what we'll be doing in our LC and RLC, is that we'll have two initial conditions. One will be the function at 0, and then the other will be the derivative of the function. And again, sometimes we'll have to do some work to figure what those are. So I know then, well, I just said it and I forgot, that I know that x prime at 0 is equal to 5. So what I need to do is find what x prime is. Now, this is where you need to make sure that you remember how to take derivatives, and I will tell you right now, I am going to be very harsh on partial credit if you don't remember how to take a derivative of this, because you have to use the product rule. I'll go ahead and write the product rule down. It's not necessary to do this. At this point in our academic careers, we should be able to just write the derivative down and then maybe simplify it. But I will remind us of the product rule. So it's the derivative of the first times the second plus the first times the derivative of the second. And then derivative of the first, this would be a2 e to the negative 2t plus a1 plus a2t times, that would be negative 2, I'll put it in parentheses, negative 2 e to the negative 2t. Now, as I said, we should be able to just write this step down right here at this point. Hopefully you can just do that at this point. Now, you could simplify it, but we're just going to be plugging in a 0 in there, so why don't we just plug in 0 right away. So we get 5 is equal to, and it's not necessary to write this step down either, but it would be 5 is equal to a2 e to the negative 2 times 0 plus a1 plus a2 times 0 times negative 2 e to the negative 2 times 0. Okay, so let's make sure we have some things here. Well, we know that this is going to go to 1, this goes to 0, the exponential goes to 1. So then, let's see what we have here. We'd have 5 is equal to a2 plus negative 2 times a1. Now, a1 was, I'm going to scroll back up here, was 3. In parentheses. So 5 is equal to a2 minus 6, and so a2 is equal to 11. Now we can write our final answer down. X at t is equal to, sorry, just spaced again, 3 plus 11t e to the negative 2t. So we have one more example problem that we need to go through, and that's of course where we're in the underdamped case. So to remind you again, this case was critically damped. Okay, so I know this randomly just appeared and forwarded up, but that's because I was having to actually come up with a critically damped case, and so I was just going ahead and looking at some of the parameters that I would need in order to ensure that this is critically damped. Alright, so just a second. Sorry about that again, there was one mistake. This should not be minus 6x prime, it should be plus 6x prime. And the other thing I want to emphasize here, I had a mistake way back here. I'll fix it and then write it down again. It was back on the previous video here. This should be negative alpha. for both of those. So I'll write it down again here, but you definitely want to go and fix that in your notes, but I'll write it down here as well. So if S1 is equal to negative alpha minus or plus j omega, it doesn't matter which one you put first here, and then S2 is equal to minus alpha minus j omega, then we get the form that x at t is equal to a1 cosine of omega t plus a2 sine of omega t e to the negative alpha t. So sorry about that mistake there, that little sign thing there, but it's very important that that's minus alpha. So basically we're expecting a negative number from this. And so I need to have this as x double prime plus 6x prime plus 13x. Now this one clearly doesn't factor, so I'm going to go ahead and pull, well first I'm going to write down my characteristic equation. S squared plus 6s plus 13 equals 0. Now again, this one clearly doesn't factor, so I'm going to go ahead and pull out the big old beast of the quadratic formula. It's not really a beast, but so s is equal to negative 6 plus or minus the square root of b squared, which would be 6 squared minus 4 times 1. I always like to emphasize because it's 4ac, and sometimes people forget to put the a in there. So 4 times 1 times 13 all over 2 times 1. And again, I emphasize that it's 2 times 1 and not just 2. Because again, if there's something in front here, that would make a very big difference. Alright, so then let's figure out what we get here. Negative 6 plus or minus, okay, I'm going to do this in my calculator real quickly. The square root of negative 16 all over 2. Now, s is then equal to negative 6 plus or minus, and in engineering, electrical engineering, our imaginary number is j. Do not use I is for current, so we have j4, because the square root of 16 is 4, and we just get the imaginary number because of the negative, all divided by 2. So s is equal to negative 3 plus or minus j2. So just to remind you here, this is my omega and this is my alpha. So my general form here, which we wrote down again already, it's going to be x at t is equal to a1 cosine of 2t plus a2 sine of 2t e to the negative 3t. And now we have to figure out what these coefficients a1 and a2 are based off of my initial conditions, which I'm going to scroll back up here. X at 0 is 5, so x at 0 equals 5. So I have 5 is equal to a1 cosine of 0 plus a2 sine of 0 e to the 0. And then, of course, cosine of 0 goes to 1, sine of 0 goes to 0, e to the 0 goes to 1. And we get really nice here that we get a right away. 5 is equal to a1. And then I believe my other initial condition, x prime, was equal to 1. Now, of course, in order to get x prime at 0 equals 1, we have to take the derivative. And let me go ahead and put the function there so we can see it. So this again requires the product rule, but instead of actually writing down the product rule, I'm just going to go and take the derivative. So we'd get, well, derivative cosine is negative, and you get a negative 2 coming out. So negative 2a1 sine of 2t plus 2a2 cosine of 2t, and then this is e to the negative 3t, and I'm not going to have space here, so I'm going to scroll down a little bit, plus, well, we don't do anything now, so this is a1 cosine of 2t plus a2 sine of 2t, and then the derivative of this would be negative 3e to the negative 3t. And now we just plug in 0. I don't know why I wrote two equal signs there. Negative 2a1 sine of 0 plus 2a2 cosine of 0 e to the 0. Give myself a little extra space here, plus a1 cosine of 0 plus a2 sine of 0 times negative 3 e to the 0. Now, yeah, there's a lot of things we had to keep track in the derivative, but all these computations here should be easy, because we know this goes to 0, this goes to 1, this goes to 1, this goes to 0, this goes to 1, and this goes to 1. So we're left with 1 is equal to 2a2 minus 3a1. 1 is equal to 2a2 minus 3, and a1 was 5. So a2, 2a2 is equal to 16, and a2 is equal to 8. And so what do we get here then? Well, my final answer, x at t, would be 5 cosine of 2t plus 8 sine of 2t e to the negative 3t. Alright, so this marks the end of just this crash course on differential equations. So we took one class period that is probably going to be several class periods in a differential equations course. But on Wednesday, we will, after we have any questions on homework covered, we will start looking at LC circuits and RLC circuits.